Hello and welcome to the GC online webinar. My name is Dr. Mazot. In this webinar, we will discuss about the most common materials used in the everyday orthodontic clinic. There are 5 major groups of materials. Bonding materials to bond brackets and other attachments on natural or covered teeth. Banding materials to bond bands on teeth. Different types of elastomeric and springs as active force elements, brackets and wires. Bonding materials are used to bond brackets and other attachments on teeth surface and other teeth with different coverage such as plastic, ceramic, zirconium and metal. There are several bonding systems in the market. The common requirements for any bonding system are optimal bonding strength, durability, cariopreventive, user-friendly, operating time, and color stability. By the literature, the optimal bonding strength is 9.7 megapascal. This bonding strength will provide a long-lasting bond under the oral environment, such as the masticatory forces, and also allow a safe removal without any damage to the enamel surface. When analyzing the bonding failure, 3 possible situations can be observed. 1. The adhesive is fully on the tooth surface, meaning that the failure was between the composite or the adhesive and the bracket base. The second possibility is the adhesive to be on the bracket base and on the tooth surface, meaning that the failure was inside the adhesive itself. The third possibility is the adhesive to be fully on the bracket base, meaning that the failure was between the adhesive material and the tooth surface. The most common bonding material to be used for orthodontic attachments are from the composite family. The BSGMA, which is composed of an organic matrix and a filler. The relationship between both components determine the viscosity and the degree of shrinkage. Both characteristics are important for the function of the composite material as a bonding material. The viscosity should be optimal to allow easy and stable attachment placement on the teeth surface. The bond to the tooth surface requires a surface preparation, using 37 degrees of phosphoric acid for mechanical bond to the tooth. No chemical bond is established. The other available and possible family are the GIC, the glass ionomer cement materials, having the advantage of containing fluoride in their composition, but seems to have lower bonding strength than the composite family. 2 common used resin composite materials are the Orthodontic by GC and the Transbond from 3M. The GC Fuji Ortho is a representative of the glass ionomer cement materials. In comparison between the glass ionomer and the resin composite materials show the following. The durability of the glass ionomer cement seems to be lower, inferior to the resin ones. The color change, both materials seems to be the same. The glass ionomer cement containing fluoride is supposed to have a karyostatic effect, which does not exist with the resin family. The bonding strength of the composite seems to be higher to the tooth surface than the glass ionomer cement. In order to shorten the procedure time by reducing steps, the self-etch primers were developed containing in their composition a weak etching material. This material was initially developed to be used on exposed dentin, but later was proposed to be used also on enamel surface. The bonding strength is inferior to the conventional etch bond systems. Today, with the developing of the new bonding materials such as the Orthodontic, the use of these expensive primers is not necessary anymore for orthodontic uses. The bonding system should be easy and friendly for the operator. optimal flow and easy dispersion of the attached base, stable seat on the attachment pad and on the teeth until curing, and maximal curing in shortest time. When using composite, the light polymerization is not that obvious. The composite under the metal attachment is not directly exposed to the light therapy and might remain uncured. For that purpose, the light curing should be done from different angulations. The enamel assists in the light curing process by the reflection from the enamel rods back to the composite at the pad of the attachment. The composite under the light activation is going a process of polymerization, creating crosslinks. The number of the formed crosslinks and the amount of material in process is determining the bond strength and the bond material quality and durability. The more material is going propagation and the more crosslinks are formed, the better is the bonding material. The process is associated with shrinkage. In conservative dentistry composite fillings, shrinkage is a source for marginal leakage and secondary caries. In orthodontics bonding brackets, this side effect is less important. In retainer wire bonding, this issue is more considered. Time, as said, it's money. Time is always an important issue also in orthodontics. The use of materials which require fewer steps, fast curing lamps are an advantage and even important in some clinical cases, such as difficult patients. Fast curing lamps can be safely used with attachments, but we need to be more careful when used for retainer wire bonding, due to the fast and more accentuated shrinkage. As mentioned, the Transbond and the OrthoConnect are resin-based materials, often used for bonding brackets and other attachments to the teeth. But also they represent two different categories of materials. The Transbond is a conventional three-step system: etching, bonding or primer, and then the bonding paste, which is applied on the bracket or attachment pad. The OrthoConnect is a new generation two-step system, in which the bonding or the primer material is not required. Besides the time saving, there are other advantages as well, such as the cost and the color change of the teeth. The use of composite system or acrylic surface is not well established. The recommendation is to use acrylic in low viscosity paste form to bond the brackets or other attachments to the acrylic crown. There is the need to remove the excess of acrylic paste before it is set. An applicator embedded in acrylic monomer fluid can be helpful to remove the excess. Monitoring the bonded bracket until the acrylic is set is required as well. The Unifast or Unifast LC and the Super C are examples for such systems. Bonding on ceramic surface is a challenge. The ceramic repair kit, including hydrofluoric acid and ceramic silane, can be used with or without the multipurpose bonding material. The required steps are the roughening of the ceramic surface using diamond burr or sandblasting with a 50 micron powder, then etch, time according to the recommendation by the manufacturer, wash and dry carefully. Apply 2 layers of silane, air dry in between the layers, and use the respective bracket bonding material. Bonding attachments on metal surface is more than a challenge and not really feasible. In those cases, the use of bands can be recommended or replaced by an acrylic surface or crown. Placing and bonding a band on a tooth is a common procedure, which requires accurate placement and the use of materials that not only withstand the treatment period, but also will not cause damage to the teeth. The best fit of the band will require minimum bonding material, just enough to fill all spaces between the band and the tooth. The bonding material should have the characteristic to bond to metal and to the tooth surface. The durability of the bonding material is extremely important to avoid washout and voids. Banding materials should have the following requirements: optimal bonding strength, durability, carrier preventive, user-friendly, and to offer the best operating time. Glass ionomer resins, such as the Fuji one, are long-time used for bonding bands. They present good bonding to the teeth and to the metal, some degree of fluoride release, and as such carrier preventive action, and can withstand the treatment time duration. The removal of the band is easy. The resin-modified glass ionomer cement was developed to offer increased strength by adding 10 to 20% of resin monomer to the glass ionomer. The resin-modified glass ionomer requires surface preparation, and the material does not present the carrier preventive effect by fluoride release. Bite opening is a common procedure with different perspectives. There are two types of targets for the bite opening. The first type is bite opening in deep bite cases, when vertical dimensions are required. The second type are bite opening in normal bite cases, when no vertical dimension changes are required. When the target of the bite opening is to open the bite block with the increase of the vertical dimension and to avoid brackets or teeth contacts, the anterior bite blocks should be placed on the lingual surface of at least 4 anterior teeth, in order not to overload the anterior teeth. The bite forces are expected to be dramatically reduced. The bite block can be prefabricated, made from metal, bite ramps, or made from composite using a silicone matrix or freehand design. When the target is bite opening without vertical dimension changes and just to avoid teeth bracket contacts, the bite blocks are placed on posterior teeth. The positioning of the bite blocks on the posterior teeth will affect less the biting force and will cause some degree of molar intrusion. There are not expected some vertical height dimension changes. 3 materials can be used for posterior bite blocks: composite-based, Compomers, or Fuji 9. The posterior bite block is placed on the upper teeth, which can offer better control of the dry field, or on the lower teeth. Upper or lower, the bite blocks must be placed on all fully erupted molars, in order to avoid unnecessary passive eruption. The recommended materials for bite blocks are Fuji 9 and resin-modified glass ionomer, which exhibit the best physical characteristics. An important advantage of the glass ionomer cement, the Fuji 9 material, it is the self-wear out of the material under the mastications, which allows a self-settle-in of the occlusion with the treatment progress. Other characteristics of the Fuji 9 to make it a very good choice for posterior bite blocks, it is the fact it is very easy to use, there is no need for surface preparation, it has some flexibility which acts like a shock absorbent, and it is made from glass ionomer cement, which offers some possibility of fluoride release. Bite opening protocol. Clean the teeth surface on which the bite block material will be placed on. Pre-adjust the vertical height using a silicone bite block, such as in Fig 1, or place a barrier, such as a handle of the applicator, such as like in Fig 2. This step is very important to allow easy and accurate bite block placement. The silicone bite blocks are pre-made to guide later the patient to the desired point. The corrode occlusion in both cases must be preserved, such as the midline. Etch and bond if required. Place the bite block material or the accessory on the tooth. Use the prefabricated bite block guide to adjust the height. Light cure or wait for setting. Remove the access and instruct the patient. The patient will experience an inconvenience for a few days, which will disappear. No TMD is expected. The handle of the plastic applicator used to guide the bite opening should be placed symmetrical, providing a secure and stable closure of the teeth without sliding, as seen in figure number 1. The plastic applicator is located posteriorly at the area of the premolar, like seen in figure number 2, for more bite opening, and is in more anterior area, as seen in fig 3, for less bite opening. Elastomeric materials are used in orthodontics for two main categories of usage: ligation and active force to execute the teeth movement. As an active force, they are considered to be indeterminate force due to the decay and the rapid change of force level delivery. Friction is another factor when biomechanical considerations are taken. Ligation. Elastic modules are the most common ligation mode, which is used with conventional brackets to place the wire inside the bracket slot. They are used also with self-ligating brackets in a limited mode in specific occasions. The elastic modules are considered in light of friction and force decay. Due to the position behind the wings of the brackets, as seen in figure number 1, the wire is forced in the slot, creating quite a high friction. In few days, the elasticity of the modulus decreases due to its decay, and the wire position in the bracket slot is not secured anymore, and the friction is changing as well. Due to that fact, the initial friction in the full arch system cannot be estimated, and it is not a stable friction, which is leading to a creation of an inconsistent, or if you want, indeterminate force system, and as such cannot be calculated or estimated in order to allow the incorporation of additional forces such as intermaxillary elastics at the early stage of the treatment. The lack of the elastic modules in self-ligating brackets is the biggest advantage of self-ligating brackets over the conventional brackets using elastic modules. Elastic chains. Elastic chains are active force to execute tooth or teeth movement. Being an elastic, they suffer the same features as the elastic modules of friction and force decay. The factors to be considered in elastic chains are exercise force. The extension of the elastic creates the force. The more is extended, the higher is the force, and the faster is the decay. The amount of extension is related to the distance between the eyes of the modules. Short or closed, medium or open, long or wide. The smaller is the distance, the more extension is required in order to place it over the brackets. The material has importance to the elastic chain force, latex or non-latex, the latex being the more resistant one. All chains suffer force decay in relation to the quality. The force decay can be up to 30% in the first 24 hours and up to 70 degrees after 1 month. This decay might lead to an unknown time in which the level of the force is not anymore adequate to exercise any tooth movement. Chains have the advantage over spring coils to allow periodontal recovery. The decay of the force allows very low forces which allow the roots to upright and the bone to heal. The recommended period to replace those chains is about 3 to 4 weeks. In the following slide, we can see one of the side effects during tooth movement under the chain or coil force, a tipping movement. The tipping creates a couple of forces due to the wire contact with the bracket occlusal and gingival walls. This movement tends to upright the roots, moving the roots in direction of the crown movement. This uprighting can happen only if the force of the tipping is decaying, reducing the friction between the slot walls and the wire. That can happen with elastics and less with springs, since the springs exercise continuous forces. In some cases, the continuous forces of the spring might lead to the binding phenomenon, which is a high friction between the wire and the slot walls and stop the teeth movement. In other cases, when the spring is placed over flexible wires, a bowing of the arch might happen. When nickel titanium closed coils are used, The spring is connected to the teeth using the spring eyelets. There are specially designed eyelets to be used with implants, with one side eyelet in different shape and size. The spring can present different forces according to the wire thickness. Nickel titanium springs exercise a continuous and constant force. The phenomenon of uprighting of the roots might not happen since there is no decrease in the force level. The friction is continuous and constant. If the friction is too high, a notching might occur due to the difference in stiffness between the wire material and the bracket material, leading to a deformation, a wounding of the wire. In that case, a locking is happening, and the only way, when the wire is replaced, the problem will be resolved. Brackets in orthodontics. Brackets are attachments with a prescription in slot to conduct the teeth movement to an optimal position of angulation, baccolingual position, and torque. There are several materials and technologies of brackets and brackets fabrications. Brackets can be made from metal, ceramic, plastic, and a hybrid of materials such as ceramic and composite. The metal brackets can be also nickel-free. There are two basic technologies to fabricate brackets: metal or ceramic injection mold and CNC, and there is a combination of both. The manufacturing process of brackets is a key for bracket accuracy and clinical performance. The metal injection mold or ceramic injection mold require an initial high investment to produce a set of cavities, the molds, in which the brackets are injected in. The fabrication process later is fast, in masses, and relatively low cost. The technique is process sensitive and presents few steps such as the debinding and sintering, which present shrinkage and might lead to inaccuracies. The quality of the initial powder and components are important as well. The CNC technique does not require any cavities. The bracket is cut out of a pre-made metal raw material. The process is slower than the MIM or SIM and more expensive. It is not technique sensitive, and the bracket's accuracy and quality are higher, but the cost for the end user is higher. Some companies with advanced technologies, such as Tomy, GC company, use a combination of the two processes, by producing the bracket using the MIM or the SIM technique, but only the slot, which is the heart of the bracket, is CNC cut. In this way, we beneficiate the advantage of both technologies, and the end user cost of brackets is lower and the quality is higher. Ceramic brackets are widely used in orthodontics, providing better aesthetics. The ceramic brackets are made from aluminum oxide. There are two types of ceramic brackets, the mono and the polycrystalline. The polycrystalline, figure number 1, is made by different procedure, ceramic injection molding procedure, leading to a lower quality of ceramic and more opaque appearance. The monocrystalline is in figure number 2, is a longer and more complicated procedure in which the aluminum oxide is melted and then cooled, serving as a raw material for the CNC procedure, leading to a higher quality of ceramic and crystal clear appearance and more expensive to the end user. The retention area at the pad of the ceramic brackets can present several options for the bonding to the tooth surface. Mechanical retention, as seen is photo number 1, or chemical retention, which provides a much higher bonding strength, as seen is photo number 2. Until today, some ceramic brackets are not easily debonded and might cause damage to the enamel surface. The removable might be causing pain to the patient and the brackets might break, leaving a substantial part of the bracket bonded to the tooth surface. A coarse diamond burr then is required to remove those remains with the risk of damaging the enamel surface. Some companies partially treat the pad to decrease the bonding strength, as seen in photo number 2. Ceramic is significantly harder than the tooth enamel. A contact between the opposing teeth with a ceramic bracket may cause wear or breakage of the enamel. Biomechanically, the ceramic brackets develop a higher friction than the metal brackets, estimated up to 30% higher, requiring the respective biomechanical consideration such as time and anchorage. The conventional ceramic brackets use clear elastic modules, which will change their color, and require more frequent decisions for replacement. Relative aesthetics is the only advantage that ceramic brackets may offer to the patient, and the use of self-ligating ceramic brackets can offer biomechanical and aesthetical benefits over the conventional ceramic brackets. Together with the brackets, wire are a basic and very important component for the execution of the orthodontic treatment. Four most common wire types are used in orthodontics: nickel titanium wires, heat-activated nickel titanium, TMA, and stainless steel. The nickel titanium wires are flexible wire with the shape memory characteristics which provide a constant deactivation force and are best suitable for the initial stages of the treatment. The new generation of thermal nickel titanium wires made possible through a new concepts and approaches of the treatment stages of the orthodontic treatment. Immediately with the deformation of the wire, in order to engage it into their irregular teeth, point number 1, the wire is being activated. At the molecular level, the metal molecules change their geometry, transforming from a passive, no-energy austenite molecular formation to the martensite molecular formation stoking energy, which is the force, which is slowly being released by the deactivation and will create the tooth movement as a reaction to the force. The curve presenting the activation and deactivation, represented by the arrows, demonstrates a long range of plateau. This straight line, the plateau, represents the quality of the nickel titanium wire, presenting a long range of constant force which is exercised on the tooth until the wire is back to its initial form. It is full deactivated, back to the austenite molecular formation associated with the tooth movement. Different quality of wires will exhibit different curves and force levels. The heat-activated thermal wires, and by some companies copper-nickel titanium wires, at room temperature can be easily deformed to be attached to the irregular teeth. Cooling the wire will make it easier the initial engagement. The deactivation phase is initiated by the change of temperature, as the wire temperature is elevating by the mouth environment, and reaching to the activation temperature, the wire is activated and starts the process of returning to the austenite phase, back to its initial shape. This characteristic offers the user high flexibility in manipulation and lower forces. The level of forces and the deactivation temperature can be also controlled by the manufacturer. The GC bioactive wires present this type of force control. A biological force distribution on the activation delivering lower forces on the anterior teeth, moderate forces at the canine and premolar area, and the highest and the molar area, according to the root's contact surface with the bone. Those highly sophisticated, high-quality wires allow a unique clinical approach, combined with self-ligating brackets, to provide a better treatment results in shorter treatment time. More information can be found in the respective webinar. The modern medicine is focused on the approach of preventing the problems instead of finding therapeutical solutions for them. In dentistry, the prevention is well known for many years, starting for oral hygiene and going through techniques and treatment protocols based on prevention. Caries and discoloration are few of those side effects that can be developed during the orthodontic treatment. Side to the oral hygiene, there are some steps of the orthodontic treatment that might lead to increase the risk for caries. The tooth surface preparation for bonding, the etching of the enamel surface. Some operators, ortho staff orthodontists, apply etching material covering much wider surface than the bracket base size. The etching of the enamel by literature is reversible, as the enamel is uptaking the required calcium or fluoride from the mouth environment. But also by research, the etching time is important. Overtime is proven to cause an irreversible damage, and the mouth environment can be not very ideal, for example the level of acidity and the presence of pigments. The control aging procedure is a benefit gained using a 3D orthodontic software to design the etch template, which can control the etched area. The etched surface is easily seen by the chalky appearance of the enamel, presenting the excellent control of the etched surface using the etching template. The brackets bonding system can be categorized into categories. The conventional one, presented by 3M Transbond XT, which is composed of fluid bonding material to be applied on the etched surface. The fluid bond is a very low-field composite material. After dispersing it on the tooth surface, it can be set using a light cure process. The second component is the bonding paste, which is a more filled material. The paste is dispersed on the bracket pad, placed on the tooth surface, and the excess is removed, followed by light curing process. The second category is represented by GC OrthoConnect, which does not require the fluid bonding material. The bonding paste is placed on the bracket pad and the bracket is positioned on the etched enamel. It is essential to sit well the brackets for maximum contact with the tooth surface in both systems. In the OrthoConnect system, it will also prevent the brackets from sliding until set, due to its lower consistency of the OrthoConnect in relation to the Transbond. In the following slide, with the high-quality photos made by my good friend Dr. Cheng from Turkey, we can clearly see on the left side tooth, photo A, the etched enamel surface is uncovered partially by any bond material. This exposed enamel is now subjected to recalcification or caries. The GC tooth mousse is advised to be used in those cases to allow the fluoride-rich environment and to increase the enamel surface resistance to caries. On the right side, we can see the fluid bonding material layer captured in the etched enamel. This layer can either be washed out or oxygenized, changing its color to yellow or brown, causing a discoloration of the enamel surface. When bonding retainer wires or other metal elements, the type of the bonding material becomes crucial. Retainers are forever, as was mentioned in 1971 film James Bond by Sean Connery, so the bonding strength is important for the long required time of function. The new bonding material from GC OrthoConnect Flow is the new and the best for bonding retainer wires. An important characteristic is the incorporation of the well-known molecule MDP, phosphoric acid ester monomer, which bonds excellent to the metal surface. In the following test, the OrthoConnect Flow exhibits double the bonding strength of Transbond LT and 1.5 times more than the Flowtain. Other important characteristics of the OrthoConnect Flow are the thixotropic characteristics, which combines excellent flow and stability, which makes the easy and clinical use, no need for bonding or primer, smooth surface, and excellent adhesion to enamel and the metal. The last topic for this webinar concerns the plastic used for clear retainers. The clear retainer is a popular choice as a retainer. There are many companies to fabricate plastic foils. The quality of the plastic foils used for the clear retainer will influence much the survival time of the retainer. Three examples of common used plastic foils are the Essex Raintree, which now is owned by Dentsply, and Zandura and Shoei Company, which are of a higher quality and more expensive than the Essex. The thickness usually used for the retainer is the 0.35 or 0.4 inches, which are equivalent to 0.75 and the 1 millimeters. Detailed information about the fabrication and processing can be found at the retainer module.